So we'll start right away. This is as usual, like last year in Sao Paulo. Feel free to ask questions. And we have the only novelty is going to be a digital blackboard, but hopefully it's comfortable enough to use it as an actual chalk blackboard. And please, David is our first speaker. We'll talk about bootstrapping the Ising stress tensor. Take it away.
Okay, thank you very much, Francesco. And thanks very much to all the organizers for giving me the opportunity to give the first talk at this exciting meeting. So I'm going to tell you about the status of a project which has been ongoing for quite some time. It's rather telling that the name of our Dropbox folder is 2020 Ising stress tensors. But nevertheless, despite some hurdles, there's a really amazing group of researchers working on this project, and they've made some incredible progress. So I will do my best to give you a status update on this project and hopefully convince you that this is worthwhile and it's starting to bear some fruit. Okay, so let me begin with some motivation. So as everyone here, I think, knows, there's been some exciting Bootstrap progress at understanding the 3D Ising CFT, mainly from the perspective of the leading Z2 odd scalar, sigma, and the leading Z2 even scalar, epsilon. So if you take the sigma sigma OPE, you get the identity operator, you get epsilon. Of course, you get the stress tensor, and an infinite tower of other operators. The stress tensor itself can be understood as belonging to the spin 2 part of the leading kind of sigma sigma double twist family, which schematically you can think of as involving 2 sigma fields with a bunch of derivatives between them, and so it's part of the leading n equals 0 tower. The sigma epsilon OPE only contains Z2 odd operators, so it contains sigma and sigma prime plus ... And so there's been some great progress by considering 4-point functions involving sigma and epsilon. So you look at all 4-point functions containing sigmas and epsilons that are non-zero by the Z2 symmetry. It was actually, we just passed the 10-year anniversary of the discovery that if you take this system of correlators, write down their crossing relations, impose some gaps that isolate sigma and epsilon, then you get an island in the allowed parameter space of delta sigma and delta epsilon. So if you don't put any gaps, you get some bound with a kink in it, and if you isolate them, you get some island. And here by isolate, we mean we put in a gap of, say, 3 for sigma prime, 3 for epsilon prime, and also this is, in fact, this is not really a 2-dimensional island. This is actually a 3-dimensional island in the allowed space of OPE coefficient ratios. So there's some OPE coefficient sigma sigma epsilon. There's another coefficient epsilon 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 showing up in these OPEs. By scanning over the possible values of this ratio, along with these 2 dimensions, you get a 3-dimensional island, and this is really the 2-dimensional projection of that. So okay, so this is, by pushing this approach further, we've gotten quite precise determinations of delta sigma and delta epsilon. So just to give some numbers, this approach has allowed us to determine delta sigma to the 6th decimal place, delta epsilon to the 5th decimal place, and is also given very precise determinations of the leading OPE coefficients. So the sigma sigma epsilon coefficient is known rather precisely, 1.0518, 537. And similarly, epsilon, epsilon, epsilon. Okay, so this is a great start. And in fact, by going into this small island, and you can look at the extremal spectrum. You optimize some OPE coefficient, look at the extremal spectrum. You can get a pretty good picture of all of the operators showing up in the sigma sigma and epsilon epsilon OPEs. Monte Carlo. This is, the error here is roughly be a factor of 20 smaller than Monte Carlo right now. So, okay, so while this is a great start, it misses some things, and so I want to highlight what this analysis is missing. So first of all, in these OPEs we wrote down, there are no parity odd operators appearing anywhere. The Ising model has a parity, space-time parity symmetry, and everything showing up in these OPEs is parity even. So we miss this whole part of the spectrum. We also miss, thanks to the selection rules, there are no Z2 even odd spin operators showing up in these OPEs. You would start to access them if you looked at the, sigma sigma prime OPE or epsilon epsilon prime OPE, but we haven't done that here. And a slightly more subtle thing is that if you look at these extremal spectra that I mentioned, as I mentioned, you kind of see several very nice trajectories. So in particular, if you look at the twist of the operators as a function of spin. So first of all, there's a leading trajectory where the stress tensor sits down here at twist 1 and spin 2, and then it kind of extends over to higher spin and asymptotes nicely to 2 delta sigma. So this is the leading sigma sigma 0, L trajectory. So you nicely see these operators in the extremal spectrum. You also see kind of very cleanly the next couple trajectories, or at least you see a trajectory which asymptotes to 2 delta epsilon, and you see another trajectory up here, which asymptotes to 2 delta sigma plus 2. And so these are like the epsilon epsilon, 0 L, and sigma sigma 1 L trajectories. So you see all this structure. Now, what you don't see are any trajectories involving the stress tensor. Okay, so there's no clear sign of kind of double twist trajectories built out of 2 stress tensors, which would asymptote to twist 2. No clear sign of kind of epsilon t trajectories or sigma t trajectories. And so these things are basically missing in the current numerics. And we have, I think, a strong sense that if we wanted to push this understanding of the Ising island and the Ising spectrum the higher precision, then we need to figure out how to get these operators to show up. Now, okay, so that's from the perspective of this Ising island, that's giving us some motivation to think more about how we could access multi-twist operators built out of the stress tensor. Now, there's also kind of separately to this story, there was some progress in the stress tensor bootstrap. Back in, going back to 2017. Well, so here, if you look at the TOPE, well, you got the identity, you get the epsilon operator, epsilon operator, with some coefficient TT epsilon. You get the stress tensor with schematically, there's some coefficient TTT. You also get parity odd operators. So like the leading parity odd scalar will show up, and so on. Now, one complication when you start dealing with the spin 2 stress tensor is that there are multiple tensor structures in the correlators. And so for example, if you look at the TTT 3-point function, it has multiple tensor structures. You can use a basis for these structures which correspond to the structures showing up in the free boson and free fermion theories. Each one of those gives a different stress tensor 3-point function, and you can use those as a basis for a more general structure. By the way, here I'm assuming my theory has a parity symmetry. If you had parity violation in your theory, then there would be an additional parity violating structure. Okay, and then on top of that, the stress tensor, well, it satisfies some word identities, so that if you integrate the stress tensor, you can get the dilatation operator, and that allows you to relate 3-point functions to 2-point functions. And so for example, there's some word identity constraint that says the sum of these couplings should equal the central charge of the theory, the coefficient appearing in the TT 2-point function. And so one thing you can do is you can come up with different ways to parameterize this constraint. In our older work, what we did is introduce some angle theta and wrote NB equals CT cos theta over cos theta plus sine theta, and F equals CT sine theta over cosine theta plus sine theta. And so with this parameterization, I automatically satisfy the word identity constraint. Basically, the upshot is that to describe these TTT 3-point functions, you have a choice. You can either describe them by specifying NB or NF, or you can specify them by saying the central charge and this additional angle parameter, theta. Okay, so now, so what kind of results did we get from the force stress tensor bootstrap? Well, one basic result is we can carve out a nice allowed region in the parameter space of delta epsilon and delta odd, and basically create a map of the world of CFTs in this space. And it looks something like this, where, you can kind of identify different theories in this space. So the free scalar theory in 3D lives up here, has a leading parity odd operator dimension of 11 because it requires a lot of derivatives and an epsilon tensor and a lot of fields. One interesting kind of surprise in this plot is that the stress tensor bootstrap seems to know something about the 3D Ising model, because there's a sharp drop in this allowed space right around delta epsilon of the 3D Ising model, 1.41. And so kind of naturally led to a conjecture that maybe the Ising sits somewhere at the top of this jump. I'll put a question mark there. Okay, so that's a guess. Of course, there are other theories we can find in this space. There's the large N limit of the ON vector models. Sits here at 7 and 2. There's a stress tensor kind of mean field theory, which sits over here at 7 and 6. Down here, there's a free Majorana fermion theory, Majorana free fermion. And over here at 4, there's a Dirac free fermion. So the shape of this sort of makes sense given where we know various theories are. And but the one missing piece to describe the shape is to understand this corner, and we've conjectured that it could be the Ising CFT. Okay, now you can also go a bit further with the stress tensor bootstrap, and for example, probe this stress tensor 3-point function coefficient theta versus the central charge. And you know, if you start putting in gaps that you expect for the Ising model, put in the delta epsilon, gap, what is theta? Theta is this parameter which I've used to parameterize the stress tensor 3-point function. Okay. So if theta equals 0, then that gives me the stress tensor 3-point function corresponding to the free boson theory. If theta is pi over 2, it gives me the 3-point function that's the 3 fermion theory. And so okay, so we can input kind of the known scaling dimensions for epsilon and epsilon prime, and ask what this space looks like, and we can get a lower bound on this theta parameter, which basically requires that if you're away from some minimum location over here, the central charge has to be very big. And we can also compare this with the known central charge for the Ising model, which sits right around here. So it's 0.99465 times the free theory value. And so you can see that by combining this lower bound with the known Ising CT, you can get some range of theta. And in fact, if you kind of go further and put in a big gap until the leading parity odd scalar that kind of goes up near this the top of this jump, say make it near 10 to 11, then you can in fact get some closed allowed region in this vicinity. So okay, so the upshot is that this analysis gave us some range for theta, which put it between about 0.01 and about 0.02. So it's not super precise, but it gave some indications. Free scalar is 0. That's right. Yeah, so this is close. This is close to the free scalar theta, which looks very reasonable. Okay, now more recently, we've realized that there's actually a lot more structure in this space. So for example, if you bound the TT epsilon OPE coefficient, and just look at what that bound does as you move around in this delta epsilon delta odd space. Okay, so it looked like this. But actually there's a lot of kind of interesting kind of peaks and ridges. Kind of schematically, you see a bunch of structure like this. So there are all these kind of, this is like a top-down view. These are all kind of ridges in the TT epsilon bound that you see in this space. And so there seems to be a lot of structure there that's very much worth exploring. Now, so just to show you one kind of slice of this that's interesting for us, interesting for the Ising model. Let's input some kind of moderate delta odd gap, which we're sure Ising satisfies, and input some delta epsilon gap so that we're honing in on the Ising spectrum. Then, okay, you see a bound in TT epsilon that has really 3 prominent kinks in it. Down here at 1, you get a kink corresponding to the free scalar solution. Up here, you get a kink. Oops. Which looks very plausibly related to the 3D Ising model. So this is at 1.41. And on the y-axis, it picks out some value of this OPE coefficient, TT epsilon OPE coefficient. Then there's actually a third kink up here, which we don't currently understand the interpretation of. So that delta epsilon is around 1.9. And so understanding that is something for, I think, for future research. Yeah.
Left plot?
That's correct. Yeah. So here I'm looking at kind of a slice where I've fixed delta odd to be bigger than 6, and so that sort of cuts along this direction. And so I'm seeing here these 3 kinks basically correspond to like this ridge, and this ridge. Yeah. Okay. So. Okay, so you see some kind of Ising kink near 0.96. And actually this can be compared with kind of independent computations of this coefficient. And so recently with Peter Tadic and Valentina Prilipina, we've been exploring the 5-point bootstrap, where we computed an estimate for this coefficient, where we came up with 0.958 plus or minus 0.007. This is some estimate of the error. It's not a rigorous error. There was also a recent computation using the fuzzy sphere methods of this coefficient. And they came up with a number that's also close, though a little bit lower, 0.916 plus or minus 0.007. Okay, so these look nicely compatible, and it looks very, this is giving us pretty compelling evidence that the stress tensor bootstrap on its own knows something about the Ising solution. Now, how do we move forward from here? This is just a kink. We would really want an island, but we also know how to get an island by looking at sigma and epsilon correlators. So the clear path forward from here is to basically try to combine the stress tensor bootstrap with the sigma and epsilon bootstrap into one big system. And so that's what we've been trying to do. Okay, now, of course, you run into various complications with this. There are lots of correlators, there are lots of tensor structures. It's a big system. But actually, it's not as bad as you might naively think. Naively, you start writing down tensor structures, and there are hundreds of them, and it looks pretty hopeless. But actually, the conservation conditions on the stress tensor mean that most of those tensor structures are not independent from each other. And there are differential equations relating the functions appearing in front of one tensor structure to the functions appearing in front of other tensor structures. And so this requires a careful analysis to decide which are the independent structures. And so okay, so for example, for TTTT, we did this analysis back in 2017, and the conclusion is that there are kind of 5 full 2-variable crossing relations. In addition to that, there are 9 independent 1-variable crossing relations, and there are kind of 4, the 1-variable relations are kind of defined along the z equals z bar line, and then there's 4 kind of constant conditions that you have to impose at the point z equals z bar equals 1/2. Okay, so the statement is that if you specify 5 of the tensor structures fully, you specify 9 of the tensor structures along the z equals z bar line, and you specify 4 of them at a point, then that's sufficient to reconstruct the full 4-point function, taking advantage of the conservation condition. Now, part of our project has been to redo this analysis for all the other correlators involving T, sigma, and epsilon. So just to give you a sense, for TTT epsilon, there are 4 full crossing relations. For TT sigma sigma, there are 6. Similarly for TT epsilon epsilon. Then there's a T epsilon 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 correlator, which has 1. There's a T epsilon sigma sigma correlator, which has 3. And then there's 5 in the T epsilon system, or the sigma epsilon system. So all in all, just to give you a sense of the size of this problem, you add these up, there are essentially 30 full crossing relations that you have to analyze. It's it's a sizable number, but it's not enormous. And this similar sized bootstrap problems have been done in the past. So this is quite tractable. Okay, now how do we how are we setting up these crossing equations? Well, in this collaboration, there are a number of Haskell enthusiasts. So there's this big Haskell code base that has been being developed. Okay, so there's a library called Hyperion Bootstrap, and a number of associated helper libraries, which can be used to set up the crossing equations, put them in a format that SDPB can solve, and manage the searches through parameter space. Okay, now the conformal blocks themselves, here we use a piece of software we also developed a few years ago called blocks 3D. And through the course of this project, the group has made a number of improvements to blocks 3D. In particular, there were a couple of bugs that had to be fixed. There was, for example, in some cases when there were extremely tiny coefficients appearing in the conformal blocks, they were getting truncated inappropriately, and that was causing the source of various numerical difficulties that we were encountering. So that's fixed. Also, it's been the parallelization of blocks 3D has been improved. The memory usage of blocks 3D is improved. And so it's a much more faster and more robust program now. We're solving the crossing equations using kind of the latest iteration of SDPB, which Vasily Doms has been helping with. And so the latest iteration, public iteration that was put out was 3.0.0. This has a much improved matrix multiplication algorithm inside of it, which makes it, say, 2.5 times faster. It also has much better kind of scaling across multiple nodes, which makes it very suitable for large-scale problems. In addition to this, oops, what did I do? Okay. This collaboration has realized that there's another improvement over the kind of standard numerical bootstrap methods that are being employed, which is related to the way that we take our conformal blocks, approximate them as some positive function times polynomials, and then to convert that into a semi-definite program, we have to sample the polynomials at some set of sample points. There's a much improved sampling method that particularly Peter and David have developed. Which both picks a better set of sample points, which are attuned to the full kind of measure appearing in the conformal block, the full function, which looks like rho to the delta over some product of poles appearing in the block. There's kind of an optimal set of sampling points you can derive based on that measure. And also uses those sampling points to construct more efficient polynomial interpolations of the blocks, which lets you reduce the order of the polynomials. In the old approach, we kind of computed the blocks to some order. That gave us some large order polynomials that we wanted to convert into a semi-definite program. And then we wanted to reduce the order of those polynomials to make it a smaller program. And concretely, the way we did that is by implementing some pole shifting algorithm, which threw out some of the poles in the blocks and then modified the residues of the poles that you kept in order to compensate. In the new method, we use these kind of optimal set of sampling points in order to construct even better lower order polynomial interpolations of the blocks. Okay, and so you can ask Peter for all the details of this method, but the upshot is that it leads to much better, say, condition numbers in the semi-definite programs. The matrices are much better behaved, and they don't have orders of magnitude between their entries, and we can get away with smaller smaller programs to solve the same problem. So for example, in one instance, a problem with a condition number of 10 to the 150 turned into something like 10 to 100 with the new method. So it's quite helpful. This is, by the way, this is the kind of initial condition number of the problem, not the condition number in the final solution. Those are also better, but not by this much. Okay, so now with that all set up, we have to search through a parameter space. And in this problem, we basically have a 6-dimensional parameter space to search through. And that consists of delta sigma, delta epsilon, and then a bunch of OPE coefficients. There's the kind of bosonic structure in TTT. There's the fermionic structure in TTT. These are all getting normalized by one of the OPE coefficients because it's only the ratios that show up in the problem. There's the sigma sigma epsilon coefficient. And there's the epsilon 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 coefficient. Okay, and here we've chosen to normalize by TT epsilon, basically because that helps make it easier to avoid the region that the stress tensor becomes completely decoupled from sigma and epsilon. But one can make other choices there and get the same results. Okay, now to search through this space, we're also using kind of modern technology. The navigator approach, based on generalized free fields, together with the skydiving method, which was developed by Eike Liu, David Simmons-Duffin, Ning Su, and Balt van Ries. And so, okay, so we have to kind of precisely define this navigator function, which is negative inside the allowed region and positive outside of the allowed region. And then if we start from some point outside of the allowed region, we can use this skydiving algorithm in order to systematically decrease the navigator and find some allowed region. So that's actually quite important in this problem because, you know, while it's easy to guess the allowed region in delta sigma, delta epsilon space, it's much more non-trivial to guess where the allowed region is in this space of OPE coefficients. And so this navigator skydive method is quite important for actually finding some allowed point in this space. Yeah. But you're asking how I'm defining this navigator? Yeah, I'll say that. So actually, precisely how you define the navigator depends on the gap assumptions that you're including in the problem. And so let me tell you about those first. Basically, we're not going to do anything too wild here. We're just assuming some basic set of gaps which let these 3 external operators be isolated. Delta epsilon prime bigger than 3, delta sigma prime bigger than 3. We're assuming the odd leading parity odd scalar is irrelevant, and we're also isolating the stress tensor in the allowed space by saying the next spin 2 operator above the stress tensor starts at dimension 4. And so to define the navigator, what we do is we take our sum rule and add to it, so we have everything appearing in the normal sum rule, and then we're going to add to it some coefficient lambda times contributions in a generalized free solution. And so in particular, we have to pick the contributions which are below the gaps that I'm imposing in my assumptions. So in this case, there's some vector at 2 delta sigma, which is below our gap. There's some contribution at 2 delta epsilon, which is below the gap. There's some contribution at delta sigma plus delta epsilon, some composite. Here we're treating sigma and epsilon as 2 independent generalized free fields, and so there's some composite operator built out of the 2 of them. And then also we need some spin 2 contributions because we've imposed this gap in the spin 2 sector. And so there's a spin 2 sigma sigma operator that we have to include, and a spin 2 epsilon epsilon operator that we have to include. So the point is that we define the navigator as kind of the minimum value of lambda, this coefficient lambda. If lambda can be 0, then we're right on the boundary of the allowed region, and we can solve our original problem. If lambda has to be positive, these contributions have to be there, then we're in the disallowed region. And so by probing the minimum value of lambda, if that's positive, then you know you're in the disallowed region of the original island. If it's negative, then you're inside the island. So that's concretely how you define the navigator. And so this is the objective in our problem. Now, okay, so how does this play out in practice? So first, we can do this at relatively low derivative order to see what happens. We're taking derivatives of the crossing relation up to some order specified by a parameter nmax, which is the maximum number of z or z bar derivatives. If nmax equals 6, then this is a small enough problem that we can kind of map out the whole shape of the island and see what it looks like. And so we get some allowed region in delta sigma delta epsilon space, which looks like this. So at this derivative order, let me tell you how big it is. This is 0.5180. This is 0.5183. This is 1.411. And this is 1.413. Okay, so it's pretty, it's small, but it's not the errors in the third or fourth decimal places here. Okay, and how does this play out in practice? Well, you pick some starting point, and in practice we managed. We picked some point here, but it was it's allowed in sigma epsilon space, but disallowed in OPE coefficient space, and then the navigator has to start moving around in OPE coefficient space to find an actual allowed point. And so, you start here, and then the navigator starts moving around. It's getting smaller and smaller and smaller, and eventually it converges to some point which is actually allowed in the space of OPE coefficients. To find the minimum of the navigator, it takes something like 115 steps of the skydiving algorithm, order 100 steps, but you can find it. And then once you find an allowed point, then you can go further and kind of try to map out the space of the island using this navigator search. And in particular, you can define a navigator function which lets you either maximize or minimize delta sigma. Okay, namely, define some function, navigator function, where you're trying to find the tips of this island. So that's something you can also do. And so if you go through that search, you just kind of start moving around like this, but then eventually you converge on the tip after another order 100 iterations. And similarly for finding the minimum value of delta sigma. Okay, and at least in this example, it's small enough that we can kind of use other methods, Delaunay searches, and so on, to map out the shape of the island and then see that the navigator is converging to the right place, the actual tips of the island. Now, when we go to higher derivative order, it's much harder to map out the full island, but we can still carry out these minimum and maximum delta sigma searches. Okay, so let me show you, I guess, the best result that we have so far. Where we push this up to nmax equals 10 and then 14, and then currently the collaboration is hard at work trying to get nmax 18 to work, but let me say how it's working so far. Well, so we can, each time we go up in derivative order, the size of this island is shrinking pretty dramatically, like an order of magnitude every shift of 4 and nmax. And so at this stage, the island's actually smaller by a little bit than our old island from the sigma epsilon mixed correlators. So this is supposed to be our old sigma epsilon island, which in this notation was computed at nmax equals 22. And so in our search at nmax 14 with the T sigma epsilon system, we again did a navigator search starting from some point like here. It moves around, goes like this, and eventually converges to some minimum point, which is allowed of the navigator. Thankfully, that minimum of the navigator is actually inside of our old island, so that gives a very good consistency check on our computations. Doing this computation, just to give you a sense, took about 140 steps in the search, and in terms of computation time, it was something like 150,000 core hours. So it's not, it's not at the millions of core hours level here, but it's a sizable numerical computation. Okay, now once we found an allowed point, we can again maximize or minimize delta sigma to try to find the extent of the island. And so where is that going? Well, basically it goes somewhere like here for the maximum delta sigma, and here for the minimum delta sigma. So it's about roughly a factor of 2 smaller than our old nmax 22 island from the sigma epsilon system. Just to put some numbers on the plot, this minimum is like 0.51814847. The maximum is 0.51814912, and then in delta epsilon space 1.4126.209, 1.4126.289. Okay, so the errors, again in kind of the sixth digit here, but it's about a factor of 2 smaller than the old determination. More exciting than shrinking these error bars by a factor of 2 is that we get actually very, very precise determinations of all these OPE coefficients involving the stress tensor, which were not known very precisely before. And so kind of using, we get, from that computation, we get ratios of OPE coefficients, but we can input the very precisely known value of sigma epsilon to get the actual magnitudes. And so, for example, this TT epsilon coefficient, which I told you before, we saw a kink around 0.96. Now we get a very tiny range for this coefficient, which is 0.95331511. So the error in this coefficient is now in the 5th decimal place. We get very good determinations of the TTT OPE coefficients, which we can parameterize either using NB and NF, the coefficients of the bosonic and fermionic structures, or the central charge and theta. But let me give you both. So now we get very good determinations of both of these numbers. And you can translate this into the central charge and theta that I mentioned before. Central charge is 0.946538. Theta is 0.01402696. So before I told you we had this indication from the TTTT bootstrap that theta was between 0.01 and between 0.02. Well, we could basically confirm that expectation here, but put the error in 1, 2, 3, 4, 5, 6, the 7th, getting down to the 7th digit. So all in all, this mixed stress tensor scalar system works very well. It's very good at getting precise data connected to the stress tensor. And we have another number of items that we intend to pursue to push this further. So immediately on our plate is to try to finish the same computation that I showed you, the skydive computation. At higher derivative order, we're setting up and running nmax equals 18 right now. I'm hopeful that this could give another order of magnitude on all the numbers. We'd really like to look at the extremal spectrum. So we'll have to bound, once we have this small island at nmax 18, we'll compute bounds on the OPE coefficient magnitude and extract the extremal spectrum. And from that, we'll be able to hopefully study these missing trajectories, TT and T scalar, trajectories, which we're missing from the extremal spectra that we get from the only scalar correlators. Another item that's probably for the immediate future is to determine this parity odd gap in the Ising model. At the present, we have a very good upper bound on this gap, computed at nmax equals 10, which tells us that it's bounded by about 10.995. Maybe 9.954. But we don't yet have a very strong lower bound on the coefficient. And so that's something we could either extract from the extremal spectrum, or we can do a dedicated computation to compute the lower bound. But that's something we'd like to do soon. And finally, as I mentioned at the beginning, there's all this other kind of apparent structure in the OPE coefficient bounds in the stress tensor system. And I think it'll be very exciting to explore that structure in the mixed correlator systems involving stress tensor and scalars, and see how other CFTs pop out as kinks or islands in that space. Okay, so with that, I will end. Thank you for your time.
So, any questions?
Is the expectation that the double trace trajectory that involve operators not in the external operators of the system crossing equations, that they will never show up in the extremal spectrum no matter how high you push the derivative order?
No, I don't have a proof. I don't have a proof of that. I think it's possible they could show up, but it's just very hard to see them and access them.
Is there any example where there's evidence suggesting that it might be visible?
I just wanted to make a comment on this. That
Please.
One thing you can show is that it's very hard. You can prove that it would be very hard to make extremal functionals, like analytic extremal functionals, which would have more than what you said, that would have additional double traces. You can like run some sort of argument where you imagine some most general kind of contour integral of the crossing equation with whatever measure you want, and just based on some kind of estimates, like, you know, you prove that the function doesn't grow, like, you can do this kind of complex analysis bounds where you estimate the number of zeros. And you can show that the most number of zeros you can hope for is accounted for by the double traces of the external guys, and it would be very hard to get external functions which have more than that. But it's not a proof, as David said.
Thank you.
Yeah.
More questions?
So, if you push the nmax to infinity, would you expect your island to shrink to a point, or for that would you need to add more operators in your bootstrap? Like you started with sigma epsilon and now you're adding t as well.
Yeah.
So would you need to add more, or?
So I think this is very closely related to the previous question. Whether these other trajectories will show up. You know, if they did eventually show up, if you pushed a very high order, then it could shrink to a point. But if in practice, I think it's going to be very hard. You know, for example, other trajectories are like, you know, there's some like epsilon prime trajectory, which that one may be very hard to see in this T sigma epsilon system. So I would expect in practice that it will not shrink to a point in this system that you would need other correlators to eventually see these other trajectories that will show up.
But could you estimate the minimum possible size of the island as a function of maybe the dimensions or structure constants?
It's a good question. I don't know how to do that at present, but it's worth thinking about. I don't know the answer.
Other questions? Well, we can then have a coffee break and thank David again.